We are glad you all made it in today to our 2021 irrigation workshop. Thank you for jumping on Zoom with us this morning. We appreciate each one of you being here. We know that irrigation is an important use of a natural resource, and we think with the meeting today, we're going to demonstrate how irrigation can be used safely to actually help protect our environment while at the same time maximizing crop yields. Today's workshop is sponsored by Kentucky Farm Bureau. They have a vested interest in water quality and water management, and this is part of their initiative in that area that's funding this effort. You're going to see a lot of research discussed today that's been funded by our commodity organizations as well. So Kentucky Corn Growers, Kentucky Soybean Board, Kentucky Small Grain Growers, Seymour Milling, and a few other local vested interests who are putting money and time and effort into irrigation as well. With that, I want to go through the format for today. And so we're going to have several speakers. We've changed this order just a little bit. So Dr. Windroth, we're going to start with him and talk about using the soils and determine when to irrigate that way. Then from that, we'll go into Matt Dixon's discussion on Kentucky climate and weather and irrigation. And then we'll get into Dr. Salmeron's discussion on crop water use and when to irrigate. And then Dr. Knott and I will finish out the session. A couple of things if you can help us out. What we'd like to do is we're going to run each of these videos. We recorded them ahead of time just to help ensure that we maintain good internet stability today. But if you would, just in the chat box, just put your name in, where you're from. That's a nice way to kind of see where everybody's at. And then as you're going through each of these presentations, if you've got questions, feel free to enter those in the chat box, and you can send them directly to me, or you can send them to the entire group. And what we'll try to do is answer a couple of those after each talk. And then we do have time at the end where we're going to have a roundtable discussion with all of the speakers, and that'll be a live session where we'll open it up for other questions that way as well. And so with that, I think I will begin our first presentation, which is Dr. Ole Windroth. Now, Dr. Windroth is a soil physicist. He's originally from Germany. He's a world-renowned expert on spatial variability and how that applies in agriculture. He's an extremely accomplished scientist, but he's also very interested in how those soil physics affect the final yield in the field. And he's very much interested in that variability. And so he's going to go through some fundamentals on soils and soil water retention and how that ultimately can help a farmer determine how to use something like variable rate irrigation. So with that, I'm going to pull up this first presentation. If there's a problem with the sound or anything like that, you may need to adjust your volume on it. If there's other issues, please let me know right away. We want to make sure that everybody is able to hear and see this as we go. So with that, we will start with Dr. Windroth.
The title of my presentation is On-Farm Irrigation: How to Use Soil Information to Decide When and How Much to Irrigate. And I want to give you an update on our variable rate irrigation research. The structure of my presentation is, first, I want to give you a brief background. Then we want to learn about soil-water relationships and how we can use them for irrigation decisions. And I will end this presentation with an update on our variable rate irrigation research. And then later, I am prepared during our roundtable or discussion session to have further talking points on mapping of soils and delineation of management zones for variable rate irrigation and computer simulation of plant and soil processes. So simple facts on the irrigation control that we want to hear about this morning. When do we turn on irrigation? How much water do we apply? And when do we turn it off? There are simple rules that I would like to share with you today that might help you to make irrigation decisions. Most of our research happens in this field. It's the Hargis field in Trevor Gilkey's Hillview Farms in Princeton, Kentucky. And this field is classified as a Kreider silt loam for most part, but you can see from the topographic elevation map of this field that we have quite a variation in topography. We have shoulders, we have back slopes and foot slopes, and with that comes a significant spatial variability of soil properties. This spatial variability is mostly caused by our typical karst landscape topography, which is typical for wide zones in the Mississippi Delta watershed. And many of you know these kinds of phenomena in your own fields. We have depressions in sinkholes where the good soil accumulates. This soil development in this field has left us with the following situation. We have a large area of this about 150-acre field that has clay contents between 15 and 20%, which is good. So these are the fertile zones in this field. And then on the other hand, we have also zones with clay contents between 25 and even more than 30%, which cause problems. You know that in such a silty area, water can infiltrate better than in these clay zones. And they are especially in back slopes. So we have to deal with a lot of water runoff. I've done some computer simulations here. Let's assume a situation where we apply 7/10 of an inch. Here I have the time axis, a few minutes after begin of irrigation. This is a typical time it takes the pivot to pass over one point. And in the low clay content soil, all the water can infiltrate. However, in the slopy area, in the back slope with high clay content soils, soon after the onset of irrigation, water is running off because the infiltration capacity has already been exhausted and no more water can infiltrate, and we have cumulative water runoff. The problem is not the 7/10 of an inch, as you can imagine. 7/10 of an inch applied over a whole day is $1 million rain, but 7/10 of an inch applied in 12 to 15 minutes causes really a problem, because the intensity is then 84 inches per day, and that is more than a millennium rainstorm. We now want to go into soil-water relationships. Many of you have probably heard, or you know what one very important soil-water characteristic is, the so-called soil-water retention curve or water release characteristic. We see on the x-axis the energy status of soil water, the soil water suction. You measure suction values, for example, with tensiometers or with watermark meters. And on the y-axis, we have volumetric soil water content, so in cubic inch per cubic inch, or simply volume per volume units. And we can see here, I've plotted this for 3 different soil types from the literature, for a silt loam, a clay loam, and a sand soil, how the relationship between soil water content and energy status looks like. For the silt loam, the green line, and for the clay loam, the red line. So how tight is water held by the soil? We can read that simply from this diagram. So if we have a volumetric water content of, let's say, 0.3, then we can tell that the energy is 20 kilopascal. So the water is held back in the soil with 20 kilopascal, or the root would have to execute 20 kilopascal in order to extract water from the soil. The drier the soil gets, the tighter is the water bound in the soil, because the pores get smaller and smaller, and the plant has to execute more and more energy. And if energy has to be applied, a lot of energy has to be applied, that comes for a price. That's the price of yield depressions. How much plant available water is in the soil? We have two limits for plant available water. The upper limit is the field capacity, which is in our soils about 10 kilopascals of suction. And the lower limit is the permanent wilting point. So we cannot say that at permanent wilting point that the soil is absolutely dry, but all the water that is left in the soil is dead water because it is not accessible for plants anymore. Plants can apply for a maximum of 1500 kilopascal of suction. And if the water is held tighter, then the plants die. They wilt irreversibly. The upper limit of the field capacity characterizes all the water in the soil that can be held in soil pores against gravity. For the silt loam soil, we have a limit here of plant available water between about 0.33 and 0.1 volume per volume, leaving us with a plant available water capacity of 0.23. For the clay loam soil, the field capacity value is about 0.33, but the amount of water at the permanent wilting point is 0.15, and that means we have only 0.18 volume per volume units of plant available water. For the sandy soil, it is even smaller. I will not talk about sand right now for time reasons. When do I need to turn on irrigation? We will stress this point during this presentation a lot. We do not want for sure to wait until the soil is down to permanent wilting point and then turn on the irrigation. That would cause a lot of stress to the plant to extract the water, and that's what we want to avoid. So by experience, we say, if this is the entire range of plant available water, so for the silt loam 0.23 and for the clay loam 0.18, we do not want to let this more deplete than 60%. So down to 60%. That means we get for the silt loam to about this pressure head value or suction value of roughly 33. And for the clay loam, we get to a little drier tension. We will look at those numbers in one of the following slides. How do we avoid over-irrigation? Well, if the soil is already very wet, we don't want to make it wetter and let it come above field capacity, because once the water gets into this range, then it is lost through deep drainage and it takes with it nutrients. Next, we want to look into some numbers here for the same soils, silt loam, clay loam, and sand. Again, the field capacity values, the same for silt loam and clay loam, and for the permanent wilting point, that's 0.1 and 0.15 for both soils, leaving us with a plant available water capacity, so the maximum storable plant available water content, this one minus that one with 0.23, or 0.18 for the clay loam, or 0.04 for the sandy soil. Now, in terms of soil water storage, what does that mean? So in terms of soil water storage for a 4-inch layer, we multiply the depth range 4-inch with the plant available water content and then end up with this plant available water storage. the maximum amount that can be stored plant available water in a 4-inch layer, leaving us for the silt loam with 0.9, the clay loam 0.7, and for the sand with less than 0.2 inches. For a 1-foot layer, like the A horizon in the soil, we almost store 3 inches of plant available water in a silt loam, and in a clay loam 2 inches, and in a sand 1/2 inch. For an entire 3-foot depth profile, we have more than 8 inches of plant available water storage in the silt loam, 6.5 inches of plant available water in a clay loam, and 1.5 inches in a sandy soil. So here we want to look again at how much plant available water is in the soil, but now we do not look at the maximum capacity, but we look at an actual situation characterized by water content or water potential measurements. First, let's look here at the reading of a water suction in an upper compartment between 4 and 12 inches. The measurement depth is 8 inches. We have 75 kilopascal. In the 16-inch layer, representing the range between 12 and 20 inches, we have 55 kilopascal. In the 24-inch depth, representing 20 to 28 inches, we have 30 kilopascal, and all this for a silt loam soil. This corresponds to a soil water content that we can easily transfer these readings back and forth with a water retention curve, 0.19, 0.2, and 0.25 volume percent of water. The soil water content at permanent wilting point, so the dead water that is included here, but it's not available, is 0.1. So we have actually only a plant available water content of 0.09, 0.11, and 0.15. We came to these numbers by just subtracting this 0.1 from each of these 3 numbers. If we multiply this with the depth range of the 24-inch profile here in this case, we end up with 2.8 inches of plant available water storage. Now, compared to the maximum plant available water capacity in a 24-inch depth zone, we have 5.5 inches of plant available water storage. So 2.8 compared to 5.5 is only 51%. Remember, I told you at 60% we need to turn on the irrigation, so it is already too dry, and irrigation should have turned on latest 9% ago already. So these irrigation limits, I want to characterize them one more time here. When do I turn on the irrigation? So given our limits of field capacity and permanent wilting point and the plant available water capacity, 60% of depleted plant available water capacity, we end up with a plant available water content of 0.14 in a silt loam, 0.11 in a clay loam, and 0.02 in a sandy soil. This represents 60% of 60% plant available water, so 40% depletion in the silt loam and clay loam, and for the sandy soil we can go down to 50%. And these 60, 60, 50 refer to 24 or a water content of 0.24, 24 volume percent in the silt loam. In the clay loam it is 0.26, and in the sandy soil 0.07. Or if you use tensiometers or matrix potential sensors, 33 kilopascal, 40 and 21 for the 3 soil types. Another reason for turning on the irrigation not too late is this characteristic, which is related to the soil water retention curve, this is the hydraulic conductivity function. And notice, please, both axes are nonlinear, so this is a highly nonlinear function. And we can tell that between saturation, where we have 10 inches per day hydraulic conductivity, and the irrigation limit, so 60% depletion when we want to turn on the irrigation, we have already a loss of hydraulic conductivity by a factor of 1,000. So if the soil gets still drier, then it gets harder and harder to turn on the irrigation and to allow the water infiltrating into the soil. We do not get the water anymore where we want it, and that causes irreversible yield depressions. So turning on not too late is a very important rule. How do we avoid over irrigation? Well, we need to stay away from the water content or soil water suction range above field capacity. So if the soil is already very wet, let's say at 30 kilopascal, we may irrigate a little, but never get above 10 kilopascal, because that would then mean water loss. How do we know field capacity? Well, we can either look it up in the literature or on a website, or you can use your soil moisture sensors if you have them out there over winter. And at the end of winter, we observe a long rainfall period. And at the end of that rainfall period, you wait for 2 more days, and then you take a reading with your sensors. And if that reading is stable for several hours, so the soil water content or suction do not change significantly, then that is an arbitrary estimate of the field capacity. It is a very rough estimate, but better than nothing. Now we want to look into a profile application of plant available water and plant water depletion. In this case, we look at a scenario with a fully developed root system. So we have a silt loam on top of a clay loam in both scenarios. And the scenario 1 is a wet condition. And later we look at a drier condition in scenario 2. We have soil water content measurements at 4 different depths representing these ranges. So the measurement depth is 4.5, 13.5, and so on. And 2 sensors stick in the silt loam and 2 in the clay loam. Given these measurements and given the permanent wilting point, again, we do the same thing as in the previous table. We subtract this value from the permanent wilting point and end up with a plant available soil water content in all the 4 measurement layers here, and multiply it with the depth range of 9 inches. So we get the soil plant available water storage and integrate that over depth, and we have a total water storage of 5.4 inches, which compared to the entire profile, plant available water capacity is 73%. So irrigation would not be necessary yet, because we are still 13% above the threshold. Now let's look to the drier scenario. For example, we are here in a different year, like 2012. Again, the same limits here, permanent wilting point, but now we have much lower plant available water content. These values minus these limits for their respective depth ranges leave us with a plant available water storage, and that is integrated up to less than 3 inches of water. 3 inches of water compared to the total plant available water storage capacity in the soil is only 40%. So irrigation should have been initiated long time ago. To give you a little impression of water storage compared to transpiration at this time of the year, when we have a fully developed root system and a fully developed corn canopy, the evapotranspiration rate is slightly less than 1/4 of an inch per day, mostly 0.4 to 0.5 inches per day, on some hot and windy days even more than that. Now we want to look at a scenario for a Kreider silt loam soil where we do not have a completely developed root system, but a corn crop that is during growth. So for that, I have prepared a little scenario that I want to initiate now. So here you can see a little calculator that we are currently developing. So let me show you first of all, this graph. We have the soil water profile, and the soil water profile depth is, let's say, 50 inches. That's the maximum root, 40 inches is the maximum rooting depth of the corn. Our fixed limits here are field capacity, which is the blue line. This is the soil water content in a 2-layer soil profile, upper part silt loam, lower part clay loam. And this water content at field capacity is the water content that can be held back by pores against gravity. On the other end, we have the permanent wilting point, and clearly you can see now the permanent wilting point is at a lower water content in the silt loam layer part of the profile, and here in the deeper layers we have clay loam, and here the permanent wilting point is already higher. This difference between field capacity, taken 60% of that difference, is denoted by the green line. So this green line is the theoretical depletion limit. Whenever the soil water gets below that limit, we need to turn on the irrigation unless roots can take up water from a different layer. So we begin here with the same scenario that I showed you in the previous table in the PowerPoint, so a wet situation. And let's assume the farmer planted corn on April 15, which was actually the case, and the current date for which we entered these soil water content values at the 4 measurement depth, that date was May 15, so a month after planting the corn, and we have a root depth already reaching down to 12.7 inches. And the root zone here is slightly deeper because we have capillary rise of water. That's why I characterized the root zone as the effective root zone. We can tell that to some depth, the measurements denoted by the black line here, the measurements are already below the 60% depletion limit. And we say, and this zone ends at 8 inches. So the calculator has given that number to us and tells us there's a deficit situation down to 8 inches soil depth. That is characterized by this part. We then have some part of the profile where the measured water content is still above the deepest rooting depth. So the roots take up now mostly from this part here. And that is why there is no absolute stress situation right now. But the calculator tells us, if we think about irrigation and want to avoid going above field capacity, then the calculator tells us the root zone, so this root zone at the moment can store an additional 1.5 inches of water. And right now the total water deficit in the root zone, that is the water deficit here in this part, and then we have still excessive water above that 60% depletion limit here, this area in the root zone. Both areas added up shows us a water deficit of 0.25 inches. Now we want to look at the second scenario, so a drier condition, and I simply copy the numbers and enter them as measurements now into this table here. And here we are. So now the measurements went down. Of course, the field capacity and permanent wilting point, they stayed the same. The root depth stayed the same. And now we have really a more serious deficit situation because the entire rooting depth is depleted far down below the 60% depletion limit. So with the same calculated rooting depth of 12.7 inches, we have a deficit situation now down to 18 inches of soil depth. So 18 inches is depth where the soil water content is below the depletion limit. The root zone could easily store, so this part of the profile up here could easily store 2.9 inches more water before it would reach field capacity. And the root zone has a water deficit of minus 1.65 inches. That is this part of the area. We can also simulate now a case, what if we had measured these sometime later, let's say a month later, and we now consider the effect of a greater rooting depth. And we get here to this point, and now we can analyze the situation in the same fashion. So this tool is currently in development, and now I will go back to the PowerPoint slides and want to give you a brief overview over our upgrading of the pivot system. So it is an about 1100 feet radius pivot, a circular pivot, and valley irrigation systems came in and they upgraded this pivot system. Jeff Franklin and Katie Pratt made a nice video. Here's a link to that video. And each of these sprinklers were exchanged, so they received shut-off valves and regulating valves that were connected through water hose and electric line. And of course, we also got a new panel. And the work that we need to do now is that we learn the tools. It's a lot of geographic information system that we create a variable rate application map. And in the research that we want to start this spring is we want to find out how precise, how exactly can we control the water application, and how much of the applied water through one nozzle do we recover in the rain gauge on the soil surface and also in the soil. And in the soil, we keep monitoring the soil water content at different depths down to 3-foot depths. We are interested in variable rate irrigation effects on crop yield, but also environmental stewardship. So at the deepest rooting or at the lower end of the rooting depth, we install tensiometers and a suction probe and take soil solution and then want to find out, do we have upward directed water movement into the root zone from below or downward directed water movement, and how well can we control that with variable rate irrigation and therefore serve the environment by reducing nitrate losses. So with that, I'd like to end my presentation and want to hear in the discussion, in the following discussion or later in the roundtable from you what is important for you to find out about variable rate irrigation and what knowledge support do you as growers expect from us UK researchers that helps you with your irrigation decisions. I want to acknowledge Trevor Gilkey, the owner of Hillview Farms, for letting us do this research in his farm, and my former graduate students, Javier Reyes, Shi Zhang, and our technicians, Mr. Wharton and Dollarhide, our department, college, and the UK Grain and Forage Center. And I would also like to thank the Soybean Board, the Southern Soybean Research Program, the Kentucky Corn Growers Association, Small Grain Growers Association, Zima Milling, and the Kentucky Farm Bureau. And with that, I thank you for your attention and look forward to your comments now in the discussion.
Okay, great. Thank you. Ola, if you're on, go ahead and turn on your video. I've got one question for you at the moment, and I think we've got time for just that one, and then we'll go into the next talk and go from there. Okay, great. And so the I think, let me see if let me look this back up. Okay. I think one of the things you made a comment in here that maybe a lot of folks don't really think about is that we can over irrigate a field pretty easily in Kentucky. And especially the fields that have some of the clay content in them. And so I think I'm going to ask the question this way, Ola, maybe a little bit different than what the person intended. And if it is, we can circle back at the session together. But if you compare our soils to, say, like a very sandy loam soil, I know you had the sandy loam retention curve on there as well. I assume a sandy loam is extremely difficult to over irrigate in terms of flooding out or pushing oxygen out of the root zone. Is that correct?
The soil that I showed with sandy texture was a pure sand. So it was really an extreme, it was a characteristic probably of a beach sand, just to show the differences. Sandy loam would be between what I showed as a sand and a silt loam, somewhere in between there. So you are right. The infiltration rate is so high that we could apply high irrigation rate and barely get any surface runoff from this soil. However, I want to remind you of the narrow range between permanent wilting point and field capacity. So that soil is, I would say, a very sensitive patient. We need to give it extra care, and I would say those soils need to be spoon-fed, very, very small portions, almost let the irrigation run all the time, but only at a rate that is similar to the daily evapotranspiration, because that soil has a lower water retention capacity. So it can hold back less water, and we have a very high danger. So the water goes quickly through the root zone, and we have a high danger of losing precious nutrients through too intensive irrigation. So I would say in that case, really the control of the soil moisture profile with a measurement would be my tool of choice, and a very good control of the applied water. And you need an extra eye on the weather forecast. So if there's any rain in the forecast, turn off the irrigation. Otherwise, if the next 3 weeks are dry, then just add the amount of water that the crop needs every day. That is my my quick answer to that question.
Okay. All right. Thank you, Ola. When we get to the roundtable discussion, remind me to ask you a question or two about the irrigation scheduler. So I think we've got some interest in that as well.
Yeah.
Appreciate that, Ola. Next up is Matt
Thank you.
Dixon. And I will get Matt's video started. Matt's been kind of busy recently. He's been doing a lot of work, putting out a lot of information about the current freezing rain, snow, and everything else that we're dealing with now. And in the middle of all this, he was able to carve out a little bit of time and put together this discussion on Kentucky climate and how that relates to irrigation with that. So we appreciate Matt's contribution here.
All right, so hi everyone. My name is Matt Dixon. I'm a meteorologist in the UK Ag Weather Center First off, I want to say that I'm recording this video on February 17th, and I hope everyone has made it through this stretch of winter weather all right. It's definitely had its fair share of impacts, especially across southeastern Kentucky, as many are still without power. This has definitely been a winter to remember, as most of our winters recently have been running mild. If you're not a fan of the cold, outlooks do hint at above normal temperatures for the end of February and start of March. But moving along, I started at UK back in 2012, unfortunately in early July when Kentucky was experiencing the worst drought in years. Since that major drought in 2012, we've been trending to a wetter and warmer climate here in the Bluegrass State. In this presentation, I'm going to talk about some of those climate trends we are seeing in Kentucky and hope to prompt some thoughts on how these changes could impact your management and production practices on the farm moving forward. So looking at a long-range forecast right now, they are lacking in accuracy at times, but something that is not lacking is climate data across the state, which gives us a way to see any climate trends being seen across the Commonwealth. I gave a similar presentation at the winter wheat meeting in early January, and I will repeat some of the information for folks that did not attend that meeting. But unlike that one, I'm going to focus this talk to the irrigation community and the climate trends we are primarily seeing during the growing season running from April through October and for the row crops of corn and beans. The two elements in the weather that play the largest factor in determining the success or failure of these crops and the associated needs for irrigation is precipitation and temperatures. So starting off, rainfall is quite abundant across Kentucky compared to many other states. In fact, the state averages over 47 inches per year based on the 81 through 2010 climate normals. I'm going to be referring to this word normal quite a bit throughout the presentation. What is a climate normal? It is essentially the average weather conditions for a particular location over a 30-year period. In this instance, I have a map of Kentucky where I show the normal annual and seasonal precip for locations across the state. These normals give us something to compare our current weather to, whether it's been above, below, or near normal. These normals also give us an idea of how to manage our farms. As I'll refer to later in the presentation, and just as an example for now, normals tell us our average last freeze date in Lexington is April 14th. They tell us how warm or cold it typically is at this time of the year. Just for instance, normals tell us the average highs today on February 17th in Kentucky lie in the middle 40s to low 50s. So compared to normal, we are running well below average for this time of year. So looking at the map, normal annual precipitation across the state ranges from around 43 inches across the northern bluegrass to closer to 50 across the southern fringes of the state. These values are based on the 81 through 2010 climate normals, and taking into account changes to our climate, these normals are updated every 10 years. The next set of normals are based on the years 1991 through 2020. These should be coming out around the middle of this upcoming summer, around July. Throughout the presentation, I'm going to show you how our climate has been trending in relation to these normals. So we'll start out with a look at precipitation. Each blue bar shows the annual average precipitation seen across the state. You can see the ups and the downs the past 100 plus years, but ultimately I want to direct your attention to the last several years on the right side of the graph. I've included a trend line on the graph, and as you can see, we are on the upward trajectory recently with 6 straight years of above normal precip here in the Bluegrass State. So in comparison to the past 125 plus years, how wet has it been recently? Well, this is a list of the top 10 wettest years on record for Kentucky with data going back to 1895. I've highlighted the years within the last decade that show up in the top 10. 5 years are included. 2011 tops the list with a state average of 64.35 inches that year. 2018 is not too far behind at just under 64. 2019, 2015, and now 2020 sits in the top 10 also. Just last year, the state averaged 57.87 inches. We compare these averages to normal, and we've been running roughly 10 to 16 plus inches above normal over those years. So bottom line, it's been trending very wet in Kentucky on a yearly basis. So how about temperatures? In this graph, I also plotted the average annual temperature of the state and added a trend line over the past 125 years. What do you see? The start of the 1900s features some cooler years across the Commonwealth, followed by increased temperatures in the 1930s. We then ran cooler with the dip in the trend line peak in the late 1960s and early 70s. Since then, we've been on quite the uphill climb. Something Chad pointed out in the winter wheat meeting, the peak in the trend line we are currently seeing is actually higher than the one we saw with the very warm years in the 1930s, which in the past we've associated with some of our warmest years on record. So how warm has it been recently? Looking at the top 10 data, again, 4 years out of the past decade, placed in the top 10 warmest years we've seen over this record, going back to 1895. The drought year 2012 sits there at number 2, with 2016-17 not too far behind. 2019 number 8. Even though you don't see 2020 on the chart, we did have another warm year last year, with the state average coming in at 57.1 degrees, good for number 17 on record. Something that I want to point out again, we are surpassing some of those years in the 1930s, which show up on this chart at number 5, 8, and 10. So now I'm going to combine the two variables of precip and temperatures to show you a trend we've been seeing through the years. In the upcoming several slides, I've included several time series scatter plots for primarily the growing season across Kentucky. In these plots, I take the average temperature and precipitation total for the state over a specific time period and plot the year on the graph. In the case of 2020 on this slide, we averaged a little over 57 degrees and almost 58 inches in precipitation last year. If you take those numbers on the X and Y axis, temperature on the X, precip on the Y, and draw a line across the graph from each, the XY coordinates meet up in the upper right portion of the chart with the year highlighted in red. I include every year going back to 1981. I then divided the data into 4 boxes separated according to the average temperature and precipitation, in this case on the annual side. Now looking at the data, any years in the box in the upper right would be years that saw above normal precip and temperatures. The top left would be years with above normal precip and below normal temperatures. Bottom left, years with below normal temps and precip, and the bottom right, below normal precip and above normal temperatures. So lastly, I then highlighted the past 5 years in red. What trends do you see on the graph? On the annual scale, the past 5 years all show in the upper right-hand box for above normal precip and temperatures. So now I'm going to take this graph, and unlike the winter wheat meeting where I showed the date by season, I'm going to now show the data for the growing season as a whole. What do you see? For the most part, we continue to see the previous 5 years in that upper right-hand corner for above normal precip and temperatures. Unlike the annual data, where we saw above normal temperatures for the year, we actually saw slightly below normal temperatures during the 2020 growing season. So, how about planting season in Kentucky, April and May? This is the one place where I saw precipitation running closer to the average normals for 81 through 2010. Every year over the past 5 is pretty close to that blue line showing average precip. 4 of the 5 years were running near to above normal for temperatures. The one exception was again 2020, which everyone remembers contained a couple late freezes for the state in the middle of April and start of May last year. More on this trend later. So in the next 2 graphs, I divide the summer into 2 different sections to show the trends over the first half of summer and the second half, the main irrigation period for the year. You see the trend continue for the months of June and July. The past 5 years have all ran above normal in precip over those 2 months, and outside of 2017, the same can be said for temperatures. While I'm on the point, I did some preliminary research on the number of days above 90 degrees for some locations across Kentucky. And while we have been trending warmer, I didn't see anything significant that we've been seeing more extreme heat across Kentucky. I also looked at some data corresponding to the number of days we saw extreme rainfall, but once again, despite years recently showing above normal rainfall, I'm not seeing a clear trend that we are seeing more extreme rainfall events. So saying that, rainfall can be sporadic spatially, so I plan on looking more into both these subjects in the future. So moving on, you see that same trend continue when I combine the months of July and August. 2016 sits quite a ways up there in the upper right-hand corner, showing that year was one of the wettest and warmest years the state has seen since 1981. Lastly, I wanted to include a look at the harvest season. While the state has seen above normal temperatures each of the past 5 years, precip has been a little bit more sporadic. While most of the events lie in the upper right-hand box again, 2017, 2019, and 2020 lie closer to the precip average for that time of year. 2018 was very wet, while 2016 you see down at the bottom right due to the drought we saw that year in September when the state only averaged 22 hundredths of an inch. So moving ahead, I now want to take a look at drought in Kentucky. This here in Kentucky, and every farmer knows, Mother Nature tosses some curveballs our way. We've seen that the past couple of weeks with the number of winter storms working through the area, and it doesn't change much during the growing season. One of those curveballs can come in the form of drought. When looking at ag, it's all about that timely rainfall throughout the growing season. We all would prefer a nice 1-inch, gentle, soaking rainfall event every week of the growing season, but it never works that way in our neck of the woods. Sometimes we are fighting torrential rainfall events and flooded fields, while other times, like 2012, it was hard to come across a tenth of an inch at times. We need a way for our crops to see a sufficient and timely water supply, and irrigation has been our answer. In recent years, we've seen some wet years here in Kentucky, saying that we still do have our fair share of abnormally dry periods that will occur during the growing season. There are two different kinds of drought: agricultural drought and hydrological drought. Ag would be the short-term drought deficits, and hydrological would be the long-term deficits where you start seeing water supply issues. As you all know, it doesn't take very long during the summer season to start seeing abnormally dry conditions if we don't see any rain. The U.S. Drought Monitor is an organization out of the University of Nebraska in Lincoln that was set up to monitor drought conditions across the United States. They have a map across the area that is released on a weekly basis showing the locations and intensity of drought across the United States. I put the link at the bottom if you're interested in looking at this map. All in all, you can see that Kentucky is in the clear right now. The worst of the drought is across the western half of the U.S. and diminishes as you move east. So what do all these colors mean? They are based on impacts being felt across the state at any particular time, whether that is short or long-term drought. So in this slide, I listed the impacts typically associated with each category in Kentucky. D0 or abnormally dry conditions in the yellow is your short-term drought impacts that are typically first to show up when it starts getting dry outside. As you can see, D0 entails lawns and vegetation starting to get brown, and crops, pastures starting to show mild stress. Intensity levels get worse from there, and D1 is your moderate drought and tan, D2 is severe, D3 is extreme, and D4 is exceptional down there in the dark red. Over half the state dipped into the severe category in October 2019 following the very dry September that year. We were seeing many of the impacts described on this page, especially low hay yields and the need of supplemental hay and water for livestock. D3 and D4 played a factor in 2012, especially across western Kentucky when long-term drought was setting in across the area and leading to supply issues. If I remember correctly that year, I think the Mississippi River was close to shutting down around our area also because of low water levels. So extreme problems in 2012. Anyways, now that we have an idea of the categories, I take you to the next slide where I show a drought time series over the past decade. As you can see, droughts are somewhat short-lived for us. Many are now calling these flash droughts. You can see these in all those spikes of yellow and tan, the abnormally dry category and moderate drought. We've really only had a couple more intense droughts since 2012, one occurring in late 2016, the other in late 2019, which is typically our dry season here in Kentucky. But by and large, they were short-lived again. I want you to see that despite us trending wetter over the past several years, we still have plenty of periods containing abnormally dry conditions. They may not last long, but they are there. So this is highlighted in the following graph. I pulled data from the U.S. Drought Monitor website to find the number of weeks each year that at least 20% of each climate division across the state listed below is consumed by an area of abnormally dry conditions during the growing season. Those columns peak in 2000, 2008, and again in 2012 with the severe droughts those years. But looking outside of those years, we do have some like 2003, 04, 17, 18, and even 20, where dry conditions were not a problem. But going with my last statement, even in the midst of a wet period, we still had several periods of abnormally dry conditions in 2019. So bottom line, irrigation has been needed in the past and will continue to be needed in the future despite a trend to wetter conditions. So next I want to take a look at frost and freezing temperatures that can impact the start and end of the growing season. Just to start off, I talked about this in the winter wheat meeting. This is a map from the Kentucky Mesnet showing low temperatures on the morning of May 9th last year. Much central Kentucky and points east had lows dip into the middle to upper 20s that night, several hours below freezing. Chad can correct me after this presentation if I'm wrong, but I believe most of Kentucky corn squeaked through this event with the growing point below the surface. Anyways, I want to point out that this event in May was rare. In the end, freezes are rare. May freezes are rare here in Kentucky, plain and simple, especially when looking at temperatures in the 20s. On the chart, I listed the last date of spring freeze for 5 locations across the state over the past couple decades. I highlighted and read the events that occurred in May. You can see that they are very few. In Lexington, you have to go back to 2005 to find the last event prior to 2020. Bowling Green and Paducah still haven't seen a freeze in May over that time span. They both were above freezing for that May event last year. It was a first for Jackson, Kentucky in 2020, and looking at Cincinnati has happened multiple times in the past with their higher latitude. Ultimately, in the end, May freezes, especially those in the 20s, are rare for most of the state. Looking at frost freeze normals, this chart is available in the extension pub I listed below. When looking at this chart, I tend to focus on the column with 50%. This would be the average day each of these locations see their last freeze in spring or first freeze in fall. Just as an example, if I look at Lexington, our average first freeze occurs on October 27th, while our average last freeze in spring occurs on April 14th. Also included is the earliest and latest freezes for both seasons, in addition to a couple categories of 10 and 90%. When using these two categories, just as an example, in Bowling Green and looking at spring frost data on the right, only 10% of the time will the last freeze occur after April 25th. Now, how are these frost freeze normals changing over the years? In the top chart, I listed the average data first freeze for the locations listed. But to show you the change in normals, I've included the data from the 1971 through 2000 normals, the current normals of 81 through 2010, and I went ahead and used a program with the Midwestern Regional Climate Center to estimate the new 1991 through 2020 normals that will come out this year. In the top chart, our climate is shifting our average first freeze a little later. For some, it's not much of a change, but looking at Bowling Green, for instance, the average first freeze date went from October 23rd in the 71 to 2000 normals to October 29th with the 91 through 2020 normals. Shifted about a week later. The same can be said about London, but in general, all the stations are seeing their average first freeze a little later in the fall season. The second chart examines spring data. What do we see here? There's a trend that our last average freeze is occurring earlier in the year. For Lexington, it shifted from April 15th in the 71 through 2000 normals to April 9th in the latest set of normals. Again, about a week difference. Cincinnati and Bowling Green saw similar outcomes. So what does this mean? For the most part, our growing season is trending longer in Kentucky. In the last chart, I listed the average freeze-free period for each station. Just from 71 to 2000 to 91 to 20, we are tacking on quite a few more days to the growing season. It's pretty significant for some locations like Bowling Green that went from 195 days to 208 days. Louisville went from 205 to 217. So all in all, our warmer climate is extending the growing season. So lastly, I wanted to bring your attention to some tools offered by the UK Ag Weather Center that might help you in your management and production practices. First is the Point Ag Forecast. This has been around for quite some time and can be accessed easiest by the blue county map on our front page at weather.uky.edu. Everything's on mobile too and is free to use on our website. In this product, the goal was to give the farmer a more descriptive weather forecast moving forward with more information than what you would see maybe by looking at that 6 p.m. newscast. So all forecast data comes from the National Weather Service and is constantly being updated by their forecasters to provide the best forecast at that time. In this point ag forecast, we took that info and broke it down into 3-hour increments to give farmers a better look at such things as the start and end time of precip, accumulations, wind speeds for spray applications, precip covers, temperatures, you name it. We then added some other rows at the bottom for the ag sector based on the forecast data above. While this tool is available for everyone in Kentucky, if we have anyone on the webinar from outside Kentucky, it is also available across the nation. So specifically for this webinar, I wanted to include this Irrigation Manager tool set. We created this tool following the 2012 drought and gives users a tool to see how much evapotranspiration has occurred at any point in the year and compare that to the accumulated precip at a gauge in your county, which in turn calculates an estimated water surplus or deficit over that specific period. In the chart below, I pulled data from Caldwell County for July 1st through the 8th last year. In the end, the location had a deficit of 0.64 inches at the end of the period. Just a little bit more information on this. Evapotranspiration, if you're not familiar with it, is a general way to see how much water and moisture your farm is losing on a daily basis based on data from the closest weather station. Right now, we use the Penman-Monteith equation to estimate evapotranspiration and currently only use a grass reference. In the future, I plan to add different coefficients to relate to other crop surfaces. So lastly is the county summaries tool where climate data can be accessed for your location at different timescales. In this chart, I take a look at the current climate data out of Lexington. Looking at the chart over the past 7 days, this location has averaged 1.46 inches, which is 65 hundredths of an inch above normal, just in one example. So we include some data from the Irrigation Manager at the end of the chart in addition to growing degree day and insect degree day estimates below. So that is where I'm going to conclude. If you have any questions, feel free to reach out at my email list on the slide. As a side note, and if you're interested, a climate webinar is hosted by the Kentucky Climate Center on a monthly basis on the first Thursday of each month. Please feel free to join, share it with others. Together with the state climatologist, we discuss the current climate conditions across the state, impacts related to those climate conditions in agriculture and water supplies, and then take a look at climate outlooks moving forward. I've included a few email addresses there on the slide to contact for getting signed up for the webinar. Otherwise, I'll also share it on my Twitter feed when the date gets closer. You can find that on our homepage at weather.uky.edu. So our next one will take place on March 4th at 2 p.m. Eastern Standard Time, 1 p.m. Central. So with that, I'm going to close up, and I wish everyone the best of luck in the upcoming growing season.
Okay, Matt, thank you for that presentation. I think a lot of folks will probably be very interested in some of the data. I know I was going through looking at the fact that we are a little bit warmer, that we're a lot wetter over this last decade relative to the last 100 years. Matt, if you're on here, I've got one question for you while we've got a moment. You can unmute and get your video on. I think the comment you made about the flash droughts, I found that to be interesting. And so maybe if you just want to expand on that a little bit, that you've got the data shows that even though we are a little bit warmer, even though we're a lot wetter, we still have drought type conditions from time to time.
Yeah, so it doesn't take much for the area, especially during those summer months of June and July, to start seeing those periods of abnormally dry conditions, that yellow color you saw in the U.S. Drought Monitor, especially whenever we start getting heat, 80s, 90s with no water coming down, can create real problems. So even though our climate is trending warmer and wetter, not only during the summer season, but throughout the year, I want you to take into account we're still going to see drier periods. We're still going to see cooler periods. The outlook for winter this past year was warmer than normal temperatures. And obviously that's not necessarily the case in February this year. So we will have fluctuations, but overall, we are looking at a warmer and wetter summer ahead. And but like I said, we will still see fluctuations in that climate. So,
okay, thanks, Matt. And Matt will be around for the roundtable discussion at the end of this as well. So we appreciate that very much, Matt. With that, we will get into our next discussion. And so Dr. Windroth went through some of the science of how the soils can help us determine when we need to irrigate. Dr. Monsi Selmaron is one of our crop physiologists, and she's going to talk more about the crop water demands itself and understanding that component and learning how to irrigate from there. Monsi's originally from Spain. She spent some time in Arkansas where they do a lot of irrigation work already. And she worked in that area quite a bit while she was there. So with that, we will jump into Monsi's presentation.
Hello everyone, this is Monse Salmeron. I'm a grain crop physiologist at University of Kentucky, located in Lexington. Today I would like to share some results from the irrigation trials that I have conducted in the last 4 years since the start of my position here at University of Kentucky. This is an outline of what I will be presenting today. First, I will show some results from corn and soybean irrigation trials that will include the yield response to irrigation, and I will briefly describe how irrigation was managed in these experiments. The next steps in the research that I've been conducting involve the use of predictive models to expand across a larger number of sites, years, soil types. So I'll be talking some about this at the end of my talk. As you know, most of grain crop production in Kentucky is rain-fed. By 2019, less than 5% of corn production was irrigated, and this number was even lower for soybean. However, the area under irrigation is increasing, and this is because on any given year, location and soil type, we might experience some amount of water stress. And quantifying these yield losses due to water stress becomes critical to make informed decisions on the need to adopt irrigation. So this is one of the questions my research program is interested in answering. Other questions are, how do we adapt management practices so we can maximize productivity under either irrigation or rain-fed conditions? And also, how do we increase environmental sustainability? And my hypothesis is that these optimal management practices will need to be tailored for producers growing grain crops under rain-fed conditions or that decide to irrigate. I will move on now to present the results from corn trials conducted in Princeton in 2017 and in Lexington during 2017 and 18. In these trials, we had both irrigated and rain-fed treatments. We supplied irrigation using a drip tape irrigation system. This allowed to have both irrigated and rain-fed treatments within the same experimental design and in the same field. We also evaluated hybrid maturities ranging from with 6 to 8 hybrids within each year, with corn relative maturities ranging from 102 to 120. We also had different seeding rates. However, for the talk today, I will focus on presenting results from a common rate of 7.8 plants per square meter. This trial received a relatively high rate of nitrogen fertilizer that was split in 3 applications in order to avoid water stress in the nutrition stress in the irrigated treatment. We manage irrigation using a daily water balance approach. In brief, this approach consists on calculating daily crop evapotranspiration using weather data to first calculate reference evapotranspiration, and then using a crop coefficient that is depending on crop development and the area of the soil that is covered by the crop. So with this, we get a daily crop evapotranspiration. Then we calculate the cumulative soil water deficit by using the deficit cumulated from the previous day, plus the evapotranspiration demand calculated for that day, and we subtract any irrigation that might occur that day. So as you can see in the figure that shows the cumulative soil water deficit, the deficit accumulates, but it goes back up and closer to 0 when there is any precipitation event. When that deficit was reduced, up to, in this case, 1.6 inches, we provide an irrigation to bring that deficit back to 0. This threshold to provide irrigation can be based on different soil types, soil depths. In our case, we were conservative in using a deficit that ensured the irrigated treatments did not experience any water stress. You can see in this slide the results from the yield response in each of the 3 environments under either irrigated in blue or rain-fed in yellow. In 2017, we had a significant yield response to irrigation in both Princeton and Lexington. However, in 2018, we did not have a significant effect of irrigation. So as you can see, the yield response was variable depending on the year and location. And for years when we experienced a response, the yield increase ranged from 17 to 56 bushels per acre. It is helpful to see where the years where we conducted the trials compare relative to other years for these locations. So in this figure, you can see the precipitation during the months of June to September in Lexington. And I've highlighted in red the years where we conducted the trials. So as you can see, these were relatively wet years with precipitation in 2018 being actually a historical record. For Princeton, the precipitation during 2017, we could consider it more as average. However, I would like you to know that it's not only important the total amount of precipitation, but the timing of the rain events is also very important. But this total precipitation already gives us a good idea of how our years classify compared to others. In this slide, you can see now some estimates of the expected economic returns from irrigation based on the field trials that we have till now. The horizontal axis shows the yield increase under irrigation, and with the vertical lines, I'm showing what was the yield increase in the 2 trials where we have a significant response to irrigation. One is Lexington 2017, that was relatively wet, still we have some significant increase in yield. And then we have Princeton 2017. The different lines in color show different scenarios of corn price going from a minimum to a maximum of corn price based on the last 10 years. So this figure gives you some estimates of what to expect on the increase in economic returns based on irrigation, taking into account that so far we have some data from a wet year in Lexington and close to a more average year in Princeton. However, these returns may change, of course, depending on a given year and location. Another question we were interested in answering is if we need to adapt hybrid maturity when we adopt irrigation. So in this figure, you can see the average yield across the 3 environments under irrigated and rain-fed conditions. And as you see, we had an increase in yield when switching from early corn relative maturity below 110 CRM to full season hybrid maturity of CRM above 110 of 34 bushels per acre under irrigated condition, but this increase in yield was lower under rain-fed conditions. So these results suggest that under rain-fed conditions, yields across hybrid maturities might be more similar, but if we irrigate, we might benefit from switching to a full season hybrid maturity. We can look more closely at data from 2017, that if you recall was a relatively drier year compared to 2018. So we see that there's this positive response of yield to increasing corn relative maturity. So we compare the yield response to corn relative maturity under irrigated conditions in range from 3 to 3.3 increase in bushels per acre per unit increase in corn relative maturity, and this value was lower under rain-fed conditions. We further investigated the effect of corn hybrid maturity with yield data for corn performance tests. That, as you know, these trials are conducted on different states, so we had readily available historical data. For this study, we selected data from Arkansas that had all sites under irrigation, and in Kentucky, all sites were under rain-fed conditions, and in Nebraska, we had a mixture where 59% of the sites were irrigated. And here you can see the results summarized for this study. In bright blue, you can see the average yield for different corn relative maturities in Kentucky. So as you can see, the best recommendations for hybrid maturity in Kentucky will range within middle corn relative maturities from the available for Kentucky, and still they will yield quite similarly. However, what we saw is that in states that have irrigation, such as Arkansas and Nebraska, there was a positive response to increasing corn relative maturity. So these results will suggest that under rain-fed conditions, producers should plant corn hybrids ranging from maybe 110 to 116 CRM, but if they decide to irrigate, they might benefit from switching to a full season hybrid maturity. And the results that we have from 2017 and 2018 also support this hypothesis. And I will continue now with results from soybean trials that were conducted for 4 years from 2017 to 2020. We also had irrigated and rain-fed treatments, and in this case also 2 planting dates, May and June, and 16 cultivars in total, ranging from cultivar maturity groups 2 to 5. We were lucky to have 2 years that were relatively dry in 2019 and 2020. So we have both dry and wet years in Lexington for these trials that evaluate the soybean yield response to irrigation. So we found yield responses to irrigation as we would expect in 2019 and 20 that were relatively dry years, but similar to the results for corn, 2017 that was relatively wet, we also saw a significant yield increase. 2018, that was a historical record of precipitation, we didn't see a positive response to irrigation. Overall, we saw that the yield response to irrigation was greater for May plantings that have a greater yield potential compared to planting soybean in June. We can look a bit more closer to results from 2019 that, if you recall, was a very wet year. And we did experience yield reductions that we attribute to excess precipitation. We had 10 days of high precipitation almost every day that were coincident with the period of pod setting, flowering and pod setting of maturity group 3 cultivars. So we believe that partially explains the reduction in yield for these cultivars, partially could be due to excess soil water, but also due to this long period of cloudy days. Also, we had excess lodging for maturity groups 5 planted in June, so they were difficult to harvest and we had complete yield losses for that cultivar. But what was interesting is we didn't see in any case a negative effect of irrigation. However, this could be the case when irrigation is managed where water is provided in excess, or in soils with poor drainage, or that are more likely to flood. This is a similar figure to what we saw earlier for corn, but in this case, I'm showing the range of yield increases that we obtained from the trials conducted during the last 4 years in Lexington. And the different colors are the different soybean price scenarios based on the minimum and maximum from the last 10 years. So these results give you an idea of what to expect in terms of the increase in economic returns when irrigating soybean, considering that the trials include some years that are dry and others that are relatively wet. However, the overall impact in the approach will also depend on the frequency of wet and dry years and on a specific soil type. So what are the questions we want to answer next? Other questions we want to address are how much yield are we losing due to water stress in a given location, not only in Lexington, and for different soil types, in wet, average, and dry years. Identify when producers in a given locations with fields with different soil types will benefit from installing irrigation and what are the expected increase in returns they could expect. And finally, identify management practices that will be tailored for rain-fed and for irrigated conditions that will reduce the risk of yield losses, for instance, under rain-fed conditions, and can help producers maximize yield when they decide to irrigate. So this approach will require, in order to answer those questions, to conduct trials over many sites, soils, and for many years, and we want to be able to provide answers sooner. So in order to do this, we are combining field trials with predictive models that will that predict daily soil water balance and crop developmental rate and growth, and that we are calibrating with the field data collected. And these predictive tools allow to then explore corn and soybean responses across a wider range of scenarios of weather, locations, soils, planting dates, cultivar, and hybrid maturities. So right now we are conducting this research and then answer questions for soybean with a recent project that was funded last year with a new graduate student. Now I will continue with the third and last part of my talk that will provide some examples of crop model applications and ongoing research using these tools. So in this slide, I provide an example that is part of the new corn management guide from the irrigation chapter in this guide, where we calculated estimates of corn water use in Princeton based on 30 years of simulations with the software DSAT. And this shows the estimated water use in blue or gray. You can see the total water use of combined water loss from the soil through soil evaporation or from the plant through plant transpiration. In red, you can see the water loss directly from the plant through plant transpiration. And the solid lines in black or red show the average across the 30 years. The useful part of using the model is that allows to also base these estimates of water use on the 30 years of weather data, not on a limited number of years. And also this was useful because quantifying water use is very challenging under field conditions and require equipment we currently do not have. And these amounts of water use have not been estimated for our climate. The data that we had was from Nebraska. So these estimates are helpful to quantify how fast soil available water will be depleted in our climate and the need to irrigate, for instance, for different soils. These are not meant as real-time irrigation tools to decide when to irrigate, but give us an idea of when soil water might be depleted on an average year or a dry, wet year. So we included this as part of the irrigation chapter, a new irrigation chapter. So this information can be then used for estimating the cumulative water deficit, like I showed earlier, and based on 30 years of weather data, in this case in Princeton, and we use two soil types. One was a clay loam soil, another a silt loam soil. And here you can see in black is the cumulative water deficit. It's average across 30 years. However, we have a high variability based on the 30 years of weather data. This variability is wide because in years that there's more precipitation, this water deficit will go back up. However, in years that are more dry, it will go down and continue to increase. And the dashed lines show when we will expect the crop to have experience water stress. The values here at the end correspond to when we consider the whole soil profile early on. The stress will occur earlier because the model, we are considering what is the rooting depth of the crop and the potential amount of soil volume that could be used to store water based on the root depth. So we can see, for instance, that under silt loam soil, we are less likely to experience water stress and not very likely before silking. The chances of water stress will be greater under a clay loam soil. Still, they will be low before silking, and we are more likely to have water stress, for instance, in 50% of the years under a clay loam soil. For the last part of my talk, I thought I would share some of the results from some exciting research in my program, where we are evaluating different models for prediction of water use and growth. This is a big team effort within the agricultural model intercomparison and improvement project, where different models around the world are running crop model simulations, and some experimentalists are providing us with valuable experimental data to test these predictive tools. We are using data from two experimental sites, one located in Nebraska and one located in Canada. The experimental site in Nebraska has both irrigated and rain-fed treatments. In each of the sites, we have data from several years, crop destructive samplings, soil moisture, and temperature data. And what is valuable from these sites is that we have early measurements from evapotranspiration or water losses from eddy covariance flux towers, which is considered the gold standard for these measurements. And these measurements are not very common under field experiments, and also not very common when combined with intensive crop destructive samplings. So this is a high quality data that is unique for evaluating model predictions. And we have a total of 11 models participating in the study with 21 different approaches to estimate water use. So it is an exciting project that we are hoping will improve the quality of predictive tools for predicting water consumption and response of crop growth and yield to water stress. In this slide, I wanted to show you just a snapshot from results from this study. And these are results, in this case, from Nebraska, from one of the years, and under irrigation. In this first figure, you can see the results from daily evapotranspiration or water losses in inches per day over the year. The data shown with the solid line is the average across all the participating models, and the shaded area in gray is the variability that we had from all the different models. It was remarkable that the average across models was very similar to the observed data predicted shown in red. This was remarkable because in this first calibration step, modelers didn't have any information on crop growth or water use. This was what we call a blind calibration. So we only provided with weather data, a soil characterization, the duration of the soybean growing season, and it was remarkable that still we were able to get very close predictions of daily evapotranspiration just with that information when we use the average across all models. In this next step, then we provided models with crop growth data from many destructive samplings of crop growth, leaf area, development, and this allowed to improve further predictions of this average across model that became closer to the observed data. And in this third calibration step, then we provide soil moisture and evapotranspiration data, and the predictions further improve, and the variability across the model shown with the gray area was narrowed. And finally, I'm not showing this information, but it was also interesting that providing this crop growth data and soil water data under irrigated conditions also improved predictions of water use and crop growth under rain-fed conditions. I'm not showing that information because that's still blind. It has not been provided to modelers, so we can really do a test of these models when they don't know the observed data, and we can test how well we can predict. I hope you found the talk useful, and please, I would like to welcome any question. And I would also like to end the talk by thanking a large group of people that has contributed to the research. Thank you, everyone.
Hey, Chad, can you hear me?
I can, Carrie. Yes.
Perfect. Do you mind if I jump in? Monty, I had a question come to me about one of your slides, and then I had a similar question about it. So
That's perfect.
When you were showing the, great, thanks. When you were showing the yield data for the different planting dates for soybean under irrigation, and you said that irrigation provided a greater yield return for the earlier planting than the June planting, right? So was the June planting double crop?
You mean if it was grown after wheat?
Correct.
No, we wanted to evaluate just the effect of planting depth and not have a confounding effect of the previous crop. So they were rotated similarly, not after wheat.
Do you think you would see any differences with that data if it were a double crop system?
I think possibly, for sure, there's going to be some effect of the previous crop. And you might have some insight about that too.
Well, I'm just really surprised and curious why you think that, you know, the June planting didn't capitalize on the water.
Oh, well, that makes total sense. Is because on May we have a higher yield potential. So that puts our threshold on how much yield we can achieve. If we don't have sufficient water, we might reduce productivity. In June, the yield potential is already lower, so there's less chances of losing yield by that time.
Okay.
On any year, it could change.
On-farm irrigation.
What did you say, Paula? I thought Paula was asking something.
That was my fault. I've got a glitch in the YouTube. I'm trying to work through at the moment. So keep talking.
I think that answered your question, Karen.
I think so. I guess, you know, not thinking through it really in depth, but for me, you know, I just always thought that with the compressed growing season of double crop soybeans or even a June planting, that even any additional water would help out, you know, mitigate that yield loss potential, right? So I was just really surprised to see
on
that.
A different year, it could be very different too. It depends also very much on the timing of the precipitation. And in fact, I'm very curious to run the simulations and see what is more likely to occur. It might be that we have a lower yield potential with June or double crop planting, but maybe it's more likely to suffer from summer water stress.
Yeah.
I think that will be a very interesting question.
Yeah, me too. All right. Thanks, Chad. I won't take up any more time.
Monty, I have a question.
Yes.
My question is, what would happen if you simulated different moisture levels in the soil as you move from wheat to the double crop soybean, i.e., many times after that wheat crop, we do not have a full profile. I don't know if you had a full profile for your June planting date, but nonetheless, what would happen indeed if we started out with a fairly dry profile?
That's a good question, because actually we've looked at 30-year simulations with a student already in a paper that got published recently with Hannah Poffenbarger and Sam Leuthold. And what we found is that corn was likely to experience excess water during the spring, and actually a negative effect of excess water that was palliated by having a cover crop. So the cover crop helped reduce some this excess water and also provided more water for later in the growing season. So with our high precipitation and having a full soil profile, we are more likely to have excess water early in the spring. And I will agree, and I'll be curious to look at that, and growing after crop, or either a winter cover crop or a wheat, winter wheat crop that the crop starts with a lower moisture, that should reduce their chances of having negative effects from excess precipitation in the spring.
Okay, thank you. I think we're going to jump into Carrie's presentation, and if there's more questions, which we encourage them, we'll circle back and do that at the roundtable discussion. And I'm also keeping track of the clock as well. I may punt on the last speaker. He wasn't that good anyhow. So I may punt on that, and we may go right into roundtable. I just want you all to know that we're cognizant of the time, and we're going to pay attention to that as well. So Monsi, thank you, and we'll see you again here in a moment for the roundtable. All speakers, I'll send you a text, or just be ready. I may, like I said, I may punt on that last presentation and go right into roundtable discussion as we look through the time.
Hello, everyone. This is Carrie Knott with the University of Kentucky. I'm the Grain Crops Extension Agronomist stationed at the Research and Education Center in Princeton, Kentucky. Today, I want to take a few moments just to share with you some preliminary results of some research we've been doing on canopy temperature in corn. And what we were trying to determine is whether we can use canopy temperature as an additional tool to help us determine when and how much irrigation is needed. As we all know, determining when to turn on the irrigation system is really critical. So over the last couple of years, we've looked at different treatments, of course, a non-irrigated control. And we also looked at 2 additional treatments. Both of those started watering at R1, and one of them ended watering at 3/4 milk line and the other at black layer. Throughout the course of this research, we had a couple of different instruments where we were using to monitor canopy temperature. The first is the scientific grade stationary instrument that remained in the field at all times and gathered information every 15 minutes. The other was a much more user-friendly version, a point and shoot camera, thermal camera, and these are not uncommon within the home inspector's realm. And so it's not uncommon for them to go out and for a home inspector to use these to determine whether or not there's enough insulation, a water leak, or other things. And kind of the cool thing about this instrument is that it gives you these visual output. And you can see here in this image, the corn leaves. You can also see the range in temperatures from 74 degrees Fahrenheit all the way up to about 95 in this image. So what we did over the course of a growing season was we went out. Every day it was sunny at noon. About noon, sometimes it was 1 o'clock. And the undergraduate student would take pictures of every single plot in this research. And so that was about 40 plots in total. And so he was out there for quite some time, each day trying to taking these images. So if you think of every day it was sunny at high noon or 1 o'clock, taking all these pictures throughout the growing season from R1 into R6, you can imagine we had thousands upon thousands of these images to go through. And so what we did at the end of the season is I sat down and said, okay, how are some ways that we can look into this data to figure it out, what we're seeing? And so first of all, I thought, well, we'll just look at the leaves. And so in this software, we could just specify lines. So I went ahead and drew lines across every leaf. The top of every leaf surface I could see and detect in all these images. And that was typically 15, sometimes 20 leaves per image. And so as you can imagine, it took us a long time. Once I got that data collected and analyzed it statistically, I was kind of disappointed because honestly, there were no statistical differences. So when you look only at the leaves, the top part of the leaves, we didn't see any differences. So I kind of went back to the drawing board and said, okay, what else can I do with this software? And what we could do is we could do the whole image. We could take the temperature of the whole image and then determine minimum, maximum, and average temperature as well. But as you can see here with this white oval, sometimes we got the sky, sometimes we got the ground, sometimes we got arms in these photographs. And so we did have to go through and still collate through this information. You can see here I just did 3 large boxes. And from those 3 large boxes, what I did was determine the average temperature, the minimum temperature, and the maximum temperature of the entire frames that excluded anything other than plants. As you can see here, unfortunately, average temperature did not differ among the non-irrigated control and the 2 treatments. And I thought, okay, that's all right. That's not too surprising. Where I thought we were going to see differences with the minimum temperature. I thought those irrigation events would bring the temperature down, but in terms of minimum temperature of the canopy, we did not see that occur for these plots. And I thought, well, okay, so all of them were about 73 to 75 degrees Fahrenheit. And I thought, well, I was a little discouraged at first. And I thought, well, the last thing we can look at is maximum temperature, those leaves of the whole frame. And so that's where we actually found some statistical differences. So I was pretty relieved because we put in a ton of work to see that actually the highest temperature was for the non-irrigated control and for the other irrigated control that ended at 3/4 milk line. You can see here that the maximum temperature for the treatment that received R1 to R6 applications of water reduced it to about 95 degrees temperature as a maximum. And so we don't exactly know the reason for that just yet, but I suspect that has to do with 2 additional irrigation treatments that occurred later in the season when it was pretty hot for the R1, R6 treatment. And that reduction later in the season, likely contributed to these lower maximum temperatures in the canopy. One thing to note, and it's a very important thing to note, the yield of these did not differ among these treatments. So although we did see some differences in maximum temperature, there were no differences in final yield. So I just quickly want to acknowledge, and not quickly, I do want to emphasize the funding provided by the Kentucky Corn Promotion Council, and then also all the hard work that the students and technicians put into this, particularly Hunter Adams. He spent a ton of time out in those fields and knew those plots quite well. Thank you very much for your attention. If you have any questions at all, please feel free to contact me. Here's my email. That's probably the best way to contact me at the moment. Also, follow me on Twitter. Throughout the growing season, I try to give timely updates of problems or issues or good things I'm seeing or hearing. So that's a good way to kind of stay on top of what I'm seeing. And as always, please visit kygrains.info for the latest up-to-date information. Thank you.
Okay, Carrie, thank you for that. Carrie, if you're on, I'll ask you a question here. And I think what the judges have decided to do is I will give about a minute overview of my presentation just with the PowerPoint here. Then I'll give you all the longer one later on that. So Carrie, go into just a little more discussion about what you thought you were going to see with that temperature and maybe what you were surprised with seeing.
Well, I really had hoped, Chad, can you hear me? My internet says it's unstable.
You're good.
Good. I really thought we'd see something, right? So we had done some work in wheat a couple of years before that and saw these striking temperature differences in wheat temperatures in the canopy that resulted in differences in yield. And of course, I know wheat's not corn, but you always hope to build upon those successes, right? And so I really had just hoped to see some differences in yield as well, which we didn't. Here's the problem, Chad. It was a really wet year. We didn't need to be irrigating that year. We were just irrigating based on a checkbook method. We weren't taking into account soil moisture. I think we over irrigated. Honestly, how do you get, one irrigation treatment at 250 and everything else at 270s? I mean, we really saturated those fields, but we really wanted to test whether or not a simple checkbook method would work. And Ola's not surprised at all that not accounting for soil hurt us, but we were just trying.
Okay. Well, and I think that's, again, you're emphasizing something that Ola mentioned too, is that we can over irrigate in Kentucky. We see a lot of national presentations on these super high yields and all of that. And it's in those type of soils that are very sandy. They may not be a true sand, but they're a sandy loam or a loamy sand. So a very different behaving soil than what we deal with over 99.9% of our crop acreage in Kentucky. With that,
and Ola, were you trying to pop in? I think Ola's trying to make a
point. Oh yeah, Ola, go ahead.
Thank you. Yeah, I'd like to add to that, Carrie, that I would say your results are very informative, and you are far from finding out nothing from this study. No, I think this study is very important and shows us very clearly what you just said. There was not such a pronounced water deficit in those seasons, and that is why we did not see any effects. But you got your tools running, so I would say it makes complete sense what you saw. So we, as scientists, of course, we always like to see differences, but if they are not put out there by Mother Nature, we should also be happy about that. And your investigation contributes substantially to an understanding of the system, and also to getting, we as a group of scientists, we get our tools ready to operate properly, and we can only hope for more extreme years. Thank you.
No, it's funny because we tell our students all the time, a non-statistical result is still an important result for science. And then when we get it, we're like, darn it, or at least that's how I am. So,
yeah,
but it still contributes to the breadth of knowledge. So,
yeah, I would like to add to that. That's still a difference. A non-statistical difference can be caused by a huge variability, but that was, I think, not the case in your study. You really diagnosed the system correctly. There was no water deficit, so the plant indicated that. Also, we have to be aware that soils show us more easily a difference. Plants always try to compensate. Thank you.
Thank you, Ola. So what I will do is very quickly on this, Carrie, you can be my timekeeper. I want this to be no more than about 90 seconds, and then we'll get into the roundtable. And so when you start getting into irrigation, you start managing a corn crop, there are some things you can do agronomically differently. There's a lot of things that people want to try to do, but in my opinion, there's two that you really want to focus on. One of those is increasing your plant population. Now we're assuming that you've got adequate moisture, you can get adequate water on the field throughout the season. And if that's the case, then you need to be at a higher plant population, probably about 36 to 42,000 in 30-inch rows. You can go up to 45,000. It's not an issue. And you should see a return on your investment in yield. Obviously, work with your seed salesmen and salespeople on that to work through some of those details. This is 38,000 in 30-inch rows. You can see we've just put in some nitrogen on the side, and that gets into the second thing that I think we can really change. I think we can really fine tune our nitrogen rates with irrigation. With irrigation, we put a huge amount of confidence that we're going to have a crop that will yield fairly well at the end of the season. And I think we can go back and look at our nitrogen uptake curve, and we can start timing out nitrogen along those lines. Some of the things we've been doing in research have been doing 3 applications, one at planting, another one about V6, and then the third one somewhere around that VTR1 stage. What we found in those studies so far is about somewhere around 220 to 240 pounds of N per acre is about all we need. We really haven't seen a benefit, an economic benefit to that, to anything higher than that. And we've been consistently getting somewhere in that 300 bushel per acre range. Now that's also with the higher populations. That component goes together in there. So we're seeing both of those things take place. I think irrigation is the one thing we can do to reduce the greatest environmental risk of nitrogen loss in a crop if we are smart about how we make that application with that. The rest of it we'll save for later. Obviously, diseases are a bigger concern. And then the final comment I'll say is irrigation doesn't fix everything. If you start out poorly, if you have sidewall compaction, if you create uneven emergence for a reason, some of those type of things, irrigation is not going to solve those problems. So irrigation solves a lot of issues, but it doesn't solve every issue. And simply adding more water is not the answer to irrigation. And I hope that's been demonstrated some today in the discussion. With that, I will end that component of it. I will put, at some point here, I'll put everything together into a play. It's already in the playlist. I'll put that playlist website. I'll link it in the chat for everyone to get access to. I noticed in Carrie's video that somehow I got a segment of Ola's video in there as well, Carrie. So I'll go back in and cut that out to where it's just your video and reload that. But if you go to that playlist, you can pick up all of these presentations there and go back and review them at that point. So let me stop sharing this screen and let's bring in our speakers. So if you all would go ahead and unmute and turn your videos on. Let me pull up a question that I know I had that came in pretty early on after Ola's talk, and so we'll start there with Ola. So Ola, in regards to over watering, do we want to try to keep our water capacity toward that 60% depletion, or do we try to keep it more toward field capacity? So how do we balance those two out?
The depletion is the trigger for turning irrigation on. So 60% means if we say that we have a tank full of gasoline with 100%, if that tank is down to 60%, then we go again to the gas station because we don't want to be stressed. We don't know exactly how long the way is and where the next gas station is. So that's a little anecdote. So the 60% is a trigger for turning it on. Also remember, if there are just the surface layers dry, but we know that roots are in layers of the soil profile that have still sufficient water, we can still sleep and rest in peace. But we need to consider the entire rooted profile and see whether we come close to the 60%. The 60% is kind of a safety margin because when, by experience, when the water gets further down, we are still above permanent wilting point, far above permanent wilting point, but a lot of metabolic energy is used up for water uptake then, and that cannot be going into production, protein or cellulosis. So from that on, we get yield depressions. The avoidance of over-irrigation, that is to avoid field capacity. And that is really important. Now you will have noticed that I put out there 0.1 kilopascal, 10 kilopascal or 0.1 bars as the field capacity limit. Many people use 0.3 bars as a field capacity. In our relatively wet climates, 0.1 bars or 10 kilopascal is a more realistic approach to field capacity. Does that answer your question, Chad?
I think it gets at what the person was asking, yes. So
Okay.
that the important thing, I think, particularly on a practitioner standpoint, is that 60% level gives us some protection against getting too dry and not being able to catch back up,
Yeah.
which is a common phrase you'll hear in irrigation, that once you get behind, you can't catch back up.
Yes.
Which makes some sense for.
I do remember your first irrigation event that you had in Princeton several years ago, and there was one of the growers, and he said, as a rule number one is, it's like going home for dinner. Don't be late. That is really important. If you wait for a long weekend, you'll never catch up, because the hydraulic conductivity drops so much, you don't get the water back into the root zone, and that way you lose nutrients. It's a very big disadvantage. So keep in mind, don't be late for irrigation.
I think that's a really good point. I've got a question for Matt. Matt, if I read through this, I think it's the fact that our normals are changing based off of what you're predicting for 91 to 2020. How significant of a change do you expect to see in those normals when looking at annual data for the state? My guess, the question's being asked in a way of, do you expect 2021 to be warmer than wetter? What do you think?
All right, so with the new normals, the current ones are 1981 through 2010. With the new normals, we're taking off that 81 through 90 data, and we're going 1991 through 2020. And as I discussed in the presentation, it was really wet. It's been really wet. It's been really warm. And just looking at some preliminary data, I know the official data, the new normals will come out in July, but it looks like our state average precipitation normal is going to increase somewhere from 47.5 inches right now to over 50 inches. Now, that does vary across the state. I noticed the bluegrass area in Eastern Kentucky was 3 inches plus, but Western Kentucky kind of surprised me a little bit. It was only about an inch difference, more than the 1981 through 2010 normals. But looking at temperatures across the board, it looks like the new normals are going to be about a half a degree warmer on the annual basis. So that's where we're at right now. Looking ahead, all the outlooks are pointing to above normal temperatures and precipitation going into the spring months and into the summer months. I know that's a long ways out. We base that a lot off climate patterns right now, especially this, you may have heard of La Nina. La Nina, cooler sea surface temperatures over in the equatorial Pacific. May not seem that far away, have an impact on our weather, but it does across the world. And usually that means above normal temperatures and precip in our neck of the woods. So that's where we're at right now, and hope that answers the question. So
I think that gets to the heart of it. As I look, we're getting close to the top of the hour, and we do want to be cognizant of that as we're finishing up. Shared on the screen should be the option for you to get in with your CC educational credit hours. Feel free to go into there. If you have questions about that, get with Colette Laurent on that, and there's her email. Most of you already know Colette and know her contact information anyhow. So feel free to do that. And then secondly, we have some other meetings coming up fairly soon. Soybean cyst nematode management and seed treatments workshop on the 25th. The IPM training school coming up on March the 10th. And in May 11th is our wheat field day, which we are crossing our fingers that this one's a real wheat field day out in the field. And that would be awesome if we get to that point and are able to do that. The idea of walking a wheat field and looking at heads just sounds pretty good at the moment. Folks, you know all of these folks. They've all posted their information their contact information. So if you've got additional questions about irrigation, about soils, crop use, any of those things, please contact us. Please let us know what how we can help you out with irrigation, and hopefully we all can help each other do a good job of managing that resource. So with that, we thank the commodity organizations and Seymour Milling and a few others for sponsoring a lot of the research. We thank Kentucky Farm Bureau for sponsoring this irrigation workshop and their commitment to water quality in the state. They have a belief that the water that we all drink should be clean, that we should be minimizing our environmental footprint whenever we can, but at the same time, farmers should have adequate access and use to that water so that we can protect livestock, crops, and that environment that we all care so much about. So with that, we appreciate you being on today. We hope that you have a safe afternoon, and we'll see you again down the road very soon. Thank you very much.